Hello?
Hello?
Hello.
Jordan? Moses?
Hello.
Morning.
Good morning.
How are you guys?
Pretty good.
I'm good as well. Got up early and meditated this morning. It was nice. How about you?
It's been going good, like usually last week is hectic typically.
Mm-hmm.
You want to force to finish at a reasonable place.
Right.
You cannot hang it on, keep it hanging, right? So,
yeah.
But I think otherwise it's all okay.
Yeah. I still have quite a bit to do to get caught up with grading, as well as with some assignments for this class. So, yeah, it'll be a good.
How is it going actually?
With
are they submitting? Because Jordan was saying that they were not submitting, correct? Students?
Yeah, I mean, last time most people submitted. There were maybe a few more students that did not submit, but also ours is with the 101 lab. It's every other week they submit a lab. So this week, well, there was going to be. We extended the due date for last week's lab to this Friday. So this will be the true test, I think. See how many lab reports come in. But
do you see any pattern that students are getting used to it, used to the new routine kind of like, or first of all, you guys, does it seem like you're getting into a routine in this way? And do you see such things in undergraduates?
I think I see a similar motivation in them that's in me as a student currently. But I think they can get away with a little bit more.
Of course.
Because, you know, I'm only dealing with labs that I'm grading for 203B. So they know how to write a lab report from, you know, the previous semester. I think most of them, now that they've been given, you know, it's hard to see where they're at because it's very easy for them to complete the labs because they're given a set of data, they're given a recording of the lab being completed. There's no real questions for them. You know, each lab has like a few questions which are mostly answered while he's describing the lab. So as long as they watch the lab and submit, just, you know. So
but you pointed out a significant thing last time that the grades have got, like the right word is dilated. I think like it's earlier the average was something and now the average has gone higher, right?
Well, in a course like that specifically, you know, in a course like this, it's a little more difficult to find an answer to a question. You can't just like type in a question in Google and an answer pop up. You have to look for specific parts, and that requires like a thought process. But in 203B, when I give a quiz, it's nearly impossible for them to not just type that into Google and have an answer, regardless of how I word the question. So before, you know, I was the way that I did the class, and I found this how my professors did it, is the lab portion, when they would do the grades for labs, it would be, that's where they're going to gain their points. And then the quizzes in the lab are where they're going to really lose their points.
Now it's
And the
the opposite.
pre-lab questions. So yeah, now it's kind of flip-flopped where I can't really ask them a question too hard because the course isn't particularly a hard course, especially because it's a pre-calculus based course. And so I can't really ask them a question that they can't find easily on Google. So that makes it a little bit more difficult, and the grades have kind of flip-flopped where, well, now they're getting all of the quiz points, and I'm trying to find ways to like take points from their quizzes, but it's very difficult. And then, so it's hard to say like, hey, did they really learn anything? It becomes difficult from, I think, instructing position. I'm not so sure.
Yeah.
And there used to be a lot more questions. There's less questions now. It's more, you know, and there's several students who just have basically turned in nothing since the chancellor came out and said, you know, you can pass or fail. Pass, fail potential.
Yeah, yeah.
And some of them who even had A's, you know, before, some have stopped submitting just because I think they realize like, well, the stuff is averaged. So as long as they turn in like 1 or 2 labs and a lab is still dropped from the original collection of labs, well, we're still in a good spot here. So they feel like they can, you know, get away with that. You know, as long as they have above a 60, they get a pass instead of having 60% on their grade. They just take a pass or fail. So it's been difficult from that perspective too. Grading has actually become a little bit more difficult too, just because you're not sure where you should be taking points, because you're not really sure if some things have been covered or if some things haven't, and you're not really sure what's going on in the classwork either. I don't know where they're at compared to where lab is. So.
Yeah, that's tricky actually. Huh. Yeah, I can see this. Like, I think I have been a little lucky, I would say, in my courses. Mostly everyone, I think things have not changed since this happened, at least the grading part. But I'm aware of situations where this can get very tricky. Yeah. Yeah. Okay, so
Great
all of us are here.
That's what's happening.
Yes, Savinash?
I said great inflation. That's what's happening.
True. Yeah. The quality going down, right? Either way. Yeah.
I think the quality has gone down both from like an instructing perspective and
True.
Student perspective. It's
feels.
If you were a paying man, you know, and you pay out of your pocket, it could be frustrating as a student who wants to learn because there's less interaction, and the quality of learning is substantially less, I would say, from a student's paying perspective. And from a teaching perspective, I think the same thing is students. The majority of students are less active in the material that they have. It's difficult, but it's a rare circumstance, I suppose. So hopefully things get better.
So, regarding the quality going down and going like, hopefully this doesn't spread into future. Have you guys got a feedback, what do you call this, evaluation form at all? Has there been any correspondence to you guys from probably the D2L or IT department saying that you will have to fill an evaluation for the courses? Typically, you have an evaluation where the instructor comes and brings in the forms, but for the last few semesters, there is also the feature of having the same thing on D2L. So have you guys got anything about it, heard about it?
I did get an email, was it yesterday? I haven't actually gone through and looked at it yet.
Okay.
But I remember seeing an email. Let's see.
Was this from the provost or was it from IT department?
Let's see.
Or it doesn't matter where it came from.
It was Dr. Talapatra. He sent.
Okay, yeah, that's what I also received. Yeah, that's to all of us, right? So what I would suggest is, as far as this course goes, I think it is important at this point. You guys should go to the evaluation. Apparently, there are 4 or 5 questions asked as to how did this semester go, how did the quality of learning go down or up. This is the place where you can point out very clearly, be very clear that if online has helped you or not, make it, because I think that survey will be used to judge how much can the university afford to go into online in the future, including fall. I think Anshula pointed out last time that, yeah, they are considering this. Yes, I got the email afterwards that, yeah, apparently they are seriously considering fall also to be, what to do with fall, whether to continue this online. So yeah, at least they should know what you guys feel like. I'll surely write. So that brings the first point that, yeah, look for evaluations on D2L. I have not got any clear instructions as to how to do that, but I'm aware that from last semester, if you go to D2L, there is a course eval. I think it's called course eval. Not sure about exactly how it goes, but just look it up. And it's just, I think it shouldn't take more than 10 minutes. And apparently there are questions related to how the online switch has worked for you guys. There's a homework 9 you have due today.
Professor suggests?
Yes.
I am looking at the survey, the course evaluation, and it says there are no surveys available to you at this time.
Okay. Well, it's also possible that it might be in the last week. I don't know. Usually it is there in the last week. I really don't know.
But this is the last week, right?
Yeah, I know. So usually it is the last week, and hopefully it shows up. I think I have information only from the email that Jordan talked about. And what I have been considering is that, okay, get the form from last time, give it to you guys as an email, and then you guys collect it together and send it as a PDF file to the physics department as an email. That's surely a possibility, but that involves me taking care. And I don't want to do anything different from what everyone is, what is happening in the university. That's also what is stopping me. So let me think about it. And how about this? If you cannot do this, don't sweat on that. But if you allow me, I might send you guys an evaluation after today. Like today is the last day of classes, last day of class for this course. If it's okay, sometime next week I'll send you guys an evaluation, and you guys send it to me. And it will be nice if you guys send me the evaluation. especially if there are questions like how did the online stuff work, give a honest opinion out there or a strong opinion if you guys have a strong opinion on it. Yeah, so let's, I'll do something about that. I started thinking about it a few days ago, but I didn't know exactly how to proceed. And there is no final exam, right? So no final exam. Is the pen writing okay? Is this readable? It is getting the last stages, right? That's okay.
Yes,
okay,
it is.
Okay. Okay. Okay, move. Okay, we introduced the variables needed for relativity last time. So it's still sort of kinematics in the sense that constant acceleration motion is still kinematics, but it can be dynamics if you think of the constant motion, constant acceleration happening due to a constant force. So in that sense, it is dynamics. So we can, we'll talk about only, we'll have time to do only one example. So this is relativistic dynamics. We'll introduce Newton's generalization of Newton's law today. Notice we have been talking in terms of 4 vectors. So we said x alpha is time, the 0th component is time, and the spatial components are the is a vector x itself. Let's say the next one was for velocity, which is c times gamma and v times gamma, right? Where gamma, let's say if we will talk in terms of beta, which is velocity over c, and gamma will be 1 over 1 minus beta square. Right, that's beta dotted with beta if you want. So these two are straight forward in a sense. Even then, there is this gamma that is coming in, so that's a slightly different from what we usually have, but velocity still remains the same. Then we talked about momentum, for momentum now. Now here, there are 2 things we will introduce. First of all, we have to define what the 0th component of for momentum is. We will define it to be energy. Right? So energy, and for dimensional reasons, it will be E over C, and there is momentum P. Right? That's a definition, and we said this is the same as since it's a it is defined as mass times U alpha, so it is simply mc times gamma and mv times gamma. It's clear that when beta tends to let's say if the, or we can also say when velocity over c is very small, then gamma approaches 1, and in that case all these quantities go back to your Newtonian physics, right? If gamma is 1, this is velocity and c. If gamma is 1, then it is mass times velocity. Here energy is mc squared in the sense that c goes up. But that should be done a little more carefully in the sense in the next order we have half mv squared, right? So that's physics in there, and this connection is important. So this is a physical interpretation here, right? We're not just collecting the terms; we are interpreting this as energy. We also defined acceleration last time. Acceleration is the derivative with respect to the invariant distance of the 4 velocity, and that gives us, remember that d by ds is equal, c times d by ds is nothing but c by dt over ds times d by dt. And that's nothing but gamma. So this is gamma times d by dt. Right, that was a useful relation we found. So we are taking the derivative with respect to the invariant distance, but that's equivalent to taking the derivative with the time in the frame we are talking about, except we have to introduce a gamma there. And in that way, acceleration becomes gamma times c. What should I do? So this becomes c times, yeah. So this is c times g gamma by dt. And when you take a derivative here, this is the same thing, c times d by dt of beta times gamma. And we took the derivative here also. We showed that a useful identity that that comes up here is what is the derivative of gamma with respect to time. We can either do that explicitly by taking the derivative of 1 over 1 minus beta square. It comes out to be equal to beta dotted with acceleration over let's say c, and then there is a gamma cube. Notice there is a gamma. When you take a derivative, this becomes 3 by 2. There's a 1 by 2, and then when you take a derivative of a square root, this becomes 3 times the square root, and that's the gamma cube showing up. And derivative of beta square is beta times derivative of velocity square is velocity dotted with acceleration, and that's this showing up. So we will we can use this in here, and that is equal to let's see, how can I write this? So this is gamma times I'll keep the gamma outside. It is useful to keep that outside because later on there will be some cancellation if we want to. But if we want to interpret it as the components of a 4 vector, then you want to keep the gamma also. So this is beta time dotted with acceleration, and there is gamma cube. So it's gamma cube. So if you want, that's a gamma 4. You can interpret it like that. If you take the derivative directly with beta, that gives you an acceleration. So it's acceleration times gamma plus, again, you have a derivative with gamma coming up, and that's plus beta times beta dotted with acceleration times this time it is gamma cube, right? Okay. And again, this is a useful identity. We will keep it, let's say here. Let me save that there. So beta dotted with okay, so that's where we were. We finished until here, and dimensionally it all seems okay. Acceleration, 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 and everything else is dimensionless. If we define what is called a proper acceleration, which is a quantity, this quantity in the rest frame. Right? Go to the rest frame, but what does it? What does the rest frame here mean? Since it is accelerating, there is this confusion that might come up that how can you accelerate if you are in the rest frame? But we are talking about inertial frames. Inertial frame means that it is going with uniform velocity, and at every instant of the time, there is a uniform velocity that you can have in the rest frame. So you're basically jumping from one inertial frame to the other inertial frame as your move as a particle is in the accelerated frame. So what that means is that you're talking in terms of local inertial frame instead of inertial frame. So that's the language you will see. It's called local inertial frame. And in that frame, you can set beta equal to 0. So this goes to 0, that goes to 0, and gamma becomes 1. So whatever is the acceleration in that frame, that's called the proper acceleration. And that has to, the length of that particular vector is the square of that quantity, and that has to remain the same, but it is not this acceleration here in that particular frame if we call it the proper acceleration here. So maybe if the length of this vector squared will be equal equal to, in any one frame you calculate the length, and since it's an invariant quantity, that works out fine. So we calculate it in the rest frame, and that is a rest frame, let's say, square, and we will call that A naught square. Like I said, so A naught is proper acceleration. And we'll bring that, we'll talk about it today again. So that's for acceleration. Next is for force, right? So we have to define what is for force. So let's define F alpha. There'll be two ways we can define this. Either we can define it as mass times the for acceleration, okay, or we can also define it as a derivative of for momentum, correct? So this is also, we can say this is C times d by ds of P alpha. Either way is okay. Maybe I should put it the other way, right? That way it matches with whatever we wrote earlier. So either you can think of it, and mass times acceleration will be on the right hand side, this when you take the derivative of this. So we can say this is C times d by ds of P alpha, right? That's like if we interpret P alpha as energy or momentum, and you can also think of it as mass times acceleration, right? For acceleration. That's perfectly fine. Am I still in the board space? Maybe move. Okay. Again, use one immediate thing, that this is the same as gamma times d by dt of P alpha, which is E over C times P. And the same thing with acceleration here, right? Acceleration is gamma, so it is m times gamma times C d gamma over dt, and C d by dt of beta gamma. Okay, so it got squeezed in there, but hopefully that can be right. And you read out, notice that gamma cancels out. So again, one should be careful if you want to interpret things as a for force. Remember, the components are important because the length of the for force is what remains the same. Then you want to keep this gamma inside with it, so that each component has a gamma in there. But if you are just interested in seeing what Newton's law is, Newton's law now has an additional component. One is, of course, the change in momentum with time is acceleration, but now the acceleration has changed its definition a little. So there are two pieces that comes in. One is this quantity here, which talks about change in energy with respect to time, and that's a power, right? So what's the zeroth component of force? Like we have been talking about zeroth component of everything here. Zeroth component of momentum is energy. Now, what is the zeroth component of force? It is energy, rate of energy, rate at which energy is being lost, and that's power, right? With the additional components of gamma in there, so that should be dealt with carefully. And this is mc, so mc square, right? Mc square. Let me say this is d by dt of mc square gamma, right? That's a definition of energy, right? Rate at which energy is being lost is given by mc square gamma. And remember, derivative of gamma we already have, right? So we can also write this as, this is equal to mc square, or let's say mc times beta dotted with acceleration times gamma cube. Usually it is harder to remember that. This is the easier because this is the old Newtonian physics itself. You just have to remember that energy is mc squared gamma. So this is the standard equation you will always see when you begin with relativity. What is the rate at which energy is being lost with respect to derivative of energy with respect to time. So that's one zeroth component of, or the content of the zeroth component of Newton's law. And we also have rate of change of momentum, dp by dt, and this is equal to now this is gamma times dp by dp, and keep the gamma out, and we have m d by dt. How does this work? So no, gamma cancels out, and we have d by dt of m v gamma. Okay. So if you want, that's this should be thought of as both the definition of momentum and acceleration playing a role. So this is equal to the force. If we know of a force that is relativistic in construction, then that's what the force is. But most of the forces we encounter in undergraduate physics, like the normal force, the force due to friction, or what are the other forces that even mg as a uniform gravity, those are not relativistic definitions. The only force that is relativistic in construction is the Lorentz force. So if you want to think of this as an example, this is q times electric field plus q times v cross b. This is good, right? Then it raises the new question as to E and B, how do they transform? So that's a lot more work in there. But what I wanted to point out is that the moment you have a force, you need to work with an example of what these forces are. And only example which is relativistic in construction is the electromagnetic force. So that's your relativistic equations, which are pretty much the same as your old equation, with the added feature that there is this gamma floating around everywhere, especially this acceleration construction. It will have more complications because there are more terms in there. But if you keep it in this form, there is a simplification that happens. So today what we will do is, we will do the simplest construction, where we will talk about a charged particle in a uniform electric field, or don't think of it as a uniform electric field, uniform force, right? Think of a charged particle in a uniform force, and presume that this is a relativistic force that we have in hand. Or more simplistically, we are talking about a particle moving with uniform acceleration. And the moment you talk about acceleration, this is the three component we are talking about. Then we have to talk about the proper acceleration. That's the only invariant concept, right? So we are talking about a particle that moves with uniform proper acceleration everywhere on its trajectory. Any questions?
I think your video is glitching.
Yeah, it says your network bandwidth is low, so it's like blurry and glitching, and slow, lagging.
Okay.
And I see a smaller video. Like, I see a smaller screen.
The video has gone smaller. Is that what it is?
Yes.
Huh.
I
How about this? Same thing with
Zoom.
Moses?
I think it's Zoom. Everybody is as small now and laggy. Yep.
No, not really, is it? It's not
Yeah,
small.
it says Angela's network bandwidth is low whenever you speak. And you're small.
Okay. Maybe.
Yeah, it's laggy for all of us. I'm not sure exactly what that means, but we could, if we.
Do you think you should disconnect and connect back? Should we disconnect
if all of
and
us
connect
cut
back?
video, will that help?
Oh, if all of us
I think
turn
it's
off
just
our
the
video,
Zoom
maybe we
thing.
can try.
You could restart the program.
Do you want me guys to try restarting the
I think we can.
Zoom again?
Maybe
Yeah,
so.
maybe.
Or can we keep going? How tolerable is
I think
keep going?
Yeah. It's
So
actually getting worse.
Let's try to restart it.
It's getting worse. So maybe restart.
Okay. So let's restart. Okay. Okay. So I'm going to restart and you'll have to re-enter again, re-enter the room again. Okay.
Yeah.
Hello?
Oh, yeah, I think it's better now.
Better? Okay,
Better, yeah.
good.
Yeah, I think it's better.
Yes, much better.
Much better. Okay. Okay. Let's see. Hopefully this stays like this. Otherwise, I cannot say that I didn't have any problem with the internet, right? On the last day, we have some. Okay. So let me keep going. So we are talking, okay, I need to move the. So we are talking about what is called motion under uniform proper acceleration, but often also called hyperbolic motion. It's in the spirit that when something is going with uniform acceleration in Newtonian physics, then you say it's parabolic motion, right? So in relativity, it instead of a parabolic motion, the trajectory is along a hyperbola, and that's why the name. So this is motion under uniform proper acceleration. And we will also assume that it's a linear motion, let's say. It's linear motion in the sense that acceleration and velocity are in the same direction. It's interesting to note that whenever you have an electric field, and if the particle starts from rest, then the motion is linear. So electric field will always accelerate or the velocity is always in the same direction as the acceleration in that case. And the counterexample is other extreme, for example, is when a particle is moving in a magnetic field. There, the velocity and acceleration is always perpendicular to each other. And both the cases can be done very nicely in the relativistic case. And this is the interesting one, or both are interesting. This is what we will do today. Probably we will have time only to cover this. So, if we go back to our equations, basically we see that we will be talking about d by dt of beta gamma, right? That's correct. And I'm thinking, what should I call this? What should I call this? Dimensions? So that is, yeah, let me not write it like this. So we have mass times velocity times so that's your momentum, and that has to be equal to force, so that's Q times E. Let's say initial velocity is 0, so V at time t equal to 0, and then everything happens in the same same direction. So we can write this to be all linear, so I can forget about everything is collinear. So velocity is parallel to acceleration. So this means parallel sign, right? So then I can forget about the vector quantity. And let me also, so this is d by dt of v, let me introduce beta there. So beta times gamma, correct? That's, we will call this Q over m times E, right? Q over m times E is an acceleration. So call it the proper acceleration, right? This is A naught, and then there is a C also, I suppose, for the dimensional reasons, right? But A naught is proper acceleration. And this is what we mean by it is moving with uniform proper acceleration. Notice again that the electric field was just brought in for context there, but we're pretty much talking about uniform acceleration, or in fact uniform proper acceleration, that is length of the acceleration and the rest frame, which is going to remain the same everywhere. Okay, so that's what this is, but now we can immediately solve this, right? This is a differential equation, and we immediately know that beta times gamma has to be moving has to be linearly changing, correct? So this is equal to A naught over C times T plus a constant. Right? That's the solution, an immediate solution. At time t equal to 0, we said that the velocity is 0. That means beta, which is having velocity in it, should be 0. So at time t equal to 0, beta is equal to 0. That means constant is equal to 0. So at time t equal to 0, and gamma is 1, and this is 0 plus a constant. That's an initial condition. That implies that constant is 0. Right, so forget this constant algebra. So we have just beta gamma is equal to A naught linearly with time. We are interested in the trajectory, so we want x as a function of time. So go back here and think of this as velocity, square this. So this is beta square over 1 minus beta square is equal to A naught square over C square times T square. Right. In fact, it is good to keep time as C square T square, right? Because that comes out with the dimension, and then I can keep C raised to 4 here. Right, it was C square, but I wrote it as C raised to 4 C square. That's just to keep track of the dimension. I'm interested in position. Position is there inside of this beta. Derivative of velocity with time is having the position. So I want to solve this for beta. So expand this out and solve it for beta, correct? So beta would be equal to, remember, so this has the structure that beta square is equal to whatever this quantity is, some capital A square minus A square beta square, right? So that gives us beta square is equal to A square over 1 plus A square, correct? So that means to say that I have a expression for beta to be equal to square of this quantity itself. So that's A naught over c square, the whole square times c square t square divided by 1 plus a naught over c square whole square times c square t square. But I'm interested actually in the square root of this because I just want this. The square root of this will be just this. And that is simply dv by dt. Oh, sorry, dx by dt, because we are talking about velocity, right? And that is a 1 over c, right? Guess 1 over c. Okay. We are interested in solving for x, so integrate this, correct? So we have a c square, I suppose, right? So dx will be x x plus a constant, let's say. Let me write it as a minus a constant, doesn't matter. Let me not think of it as initial position. It's some constant, integral constant. I can write it on the right hand side also. And this is equal to integral of so this is a constant a naught over c square times there is a c square again, right? dt. Probably not necessary to keep the c square, but just keeping the dimensions, I suppose.
Can you move the camera down?
Move the camera, sorry. Yeah. Thank you. Yeah, sorry, I started thinking as to what I'm supposed to do next. Okay. And then this is 1 plus a naught square, a naught over c square times c square t square. Oh, there's a t also there. Forget that. There's a c square t dt. So there's a c that's coming from here, so it's c square, and then there's t dt. Right? And it has the correct dimensions, I think. Help. So that's distance. There is a distance square. Is that all correct? Help here. A naught over c square. Why did I started writing a naught over c square? That's because it has a dimension of distance, I suppose. A naught over c square is having velocity cancels, or the 2 times cancels out. Yeah, so this is having the dimensions of 1 over distance, maybe. Right? Are my dimensions all correct? Give me help here. Yeah, so that's correct.
A naught over c square is 1 over meter.
1 over length, right? Yeah, 1
yes.
over length. Okay, so that's length, 1 over length. Yeah, then it's okay. So 1 over length square, length square. Yeah, I think everything is good here, except there are lots of c's floating around, but that's okay. And there was a square root. Right? Okay, thank you. Just checking on that. And let's make the substitution 1 plus a naught over c square whole square c square t square is equal to what should we call this? T or t we have already used up, s, let's say. Okay. And differentiation of that will be a naught square. Again, keep it as it is, c square whole square c square 2t dt, right? 2t dt is equal to ds. Right? So t dt is what is there in the numerator. So let me write it again. I have to go to the other board, so you guys will lose this part. So have you guys copied this? So you will have to look into your notes. Shall I move the board?
I'm good.
Okay.
Yeah, you're good.
Okay, thanks. Okay. So then we have x as a function of time now, minus an integral constant that's equal to a naught over c square times c square t dt, right? So 1 a naught over c square remains outside, correct? And the factor of 2 also has to come out. And everything else is ds apparently. And this is square root of s. That's it. And we don't have to worry. Yes, please.
Should it not be c square over a naught?
Oh, should it be? Oh, that's better because then I have the dimensions correct. No.
Because we are trying to square a naught over c square, right? So we can substitute
you're right.
ds.
Perfectly right. Yeah, and there is a length coming in, right? So there's a c square over a naught. That's correct because dimensionally we said this is 1 over length, so this is now it becomes length. Good. Thank you. And s I guess is dimensionless. Yeah, please.
And should it not be 1 over 2, not 2?
And 1 over 2, of course. Good. Thank you. Thanks for catching that. Otherwise, I would have messed up. Yeah. And we don't have to worry about the limits because we put a constant in front, right? If we are not put the constant, then we have to worry about the limits, which is also okay. This is an integral, easy integral to do, right? So this is s raised to minus half. That makes the integral plus half. So that makes it square root of s. But then it comes up with a factor of half in the denominator. That cancels the 2. So this is pretty much x of t minus constant is equal to c square over a naught times the square root of s, but the square root of s is actually square root of 1 plus a naught over c square, the square of it times c square t square. Nice. Okay, that's your solution, except for this constant. And now at this point, I have to give an initial condition. We started with the initial condition that the charge we are talking about starts from rest. I can also say that it starts from the origin. For example, at t equal to 0, it is at the origin, which is perfectly fine. But we will, to make the equations more transparent, or since I want it in a certain form, let me say that at t equal to 0, the position is actually c square over a naught itself. Like, since it has a dimension of length, let's say that it doesn't start from the origin, it starts from a specific place on the x-axis, and you will see what that represents. That just makes our equations nice. Otherwise, the hyperbola will pass through the origin, and hyperbola usually doesn't pass through the origin. So you have to shift the origin then. So I'm taking care of that here. If that is the case, then I have put this condition in there. So this is c square over a naught minus the constant is equal to, at t equal to 0, I simply have c square over a naught. This again implies that the constant, new constant, that's equal to 0. Right? If that is equal to 0, then I can rewrite this equation as expand this out. So this is x of x square as a function of time now. That's equal to, constant is 0. And put this inside. So I'm squaring this. So this becomes c square over a naught square. Right? And I'm multiplying it with 1. So when this goes inside, this cancels this out, and plus c square t square. That's nice, because now what it says is that the equation is x is square root of this, or better, if I were to write this as minus c square t square, let me write this as c t square, that's equal to c square over a naught square. Remember, if you have two variables and if you add them together, and if that remains a constant, that's a equation of a circle. And if you were to subtract them, and if that remains a constant, that's the equation of a hyperbola, right? So what this equation represents is, so let me draw this. So that's your time axis, and that's your x-axis, and this is time axis scaled with speed of light. And this is a straight line that represents the speed of light itself starting from origin would go in that direction. And if the light was coming from the past, it would go through the origin. At t equal to 0, the position, that is a fixed position, which is given by c square over a naught. That's our choice of a constant. So that is a fixed position. At time t equal to 0, it starts from somewhere here. Let's choose that to be positive. And a hyperbola that passes through that point is what the trajectory is. And that looks like this. Right. So this is how it will look like. Don't confuse the, I had mentioned that earlier, simply because a trajectory is in the space-like part in the cone doesn't mean anything. Always you have to, you're talking about on the trajectory. Right? So this trajectory is inside the light cone in the time-like part of the light cone. Always the trajectory will be in the future or in the past of the world line of a particle will always go through the time-like part of the cone. But in this case, the trajectory itself sits in the space like that has no meaning, right? That doesn't mean anything. It is a vector that is important. If you were to project it backward, this will look like this. So if you were having a Newtonian particle, if you were to accelerate it sufficiently, or if you wait for it long enough, eventually it will go faster than light, right? Because it is constantly accelerating it, eventually it will go faster than light. But here, this particle cannot go faster than light. It will keep increasing its speed, but eventually the amount it will speed will get slower and slower, and the maximum it can get is the speed of light itself. It is good to see. How do we see the Newtonian trajectory out of this? So we can actually take an approximation. So let's go back to our equation here and write this as a function x of t is equal to square root of c square over a naught square c square t square. Right, that's your trajectory written as a function of time. Pull this out. That's what we did somewhere here, right? So there's a c square over a naught, and it is also, I can think of this as some x naught here, right? So this is, let me call x naught as c square over a naught, right? So that way there's this slight simplification in this, or there's less clutter. That's the only thing, nothing changes, right? So this is x naught square. In this way of looking at it, x naught is also the position at time t equal to 0. Let me pull that out. So that's x naught square root of 1 plus c square. Let me now c t. At this stage, it is possible to think of an approximation in which this quantity in brackets is less than 1 or very much less than 1, let us say. So if we are talking about time, so let's talk about the times when this is very much less than x naught over c. Like, like the particle starts from the origin, and we are talking about times when it has not gone very far away. Whatever this quantity we constructed, it is related to the proper acceleration. Let me write that more explicitly. So this is c squared over so whatever is the proper acceleration divided by c, that is a distance in the or time in the picture in that case, and that time should be very much small or very much large compared to the scale, time scale within which you're observing the particle. In that case, I can expand this square root out, and that's equal to, so this is equal to.
Just do a binomial expansion.
Yes, think of it as just a binomial expansion, and we're talking about 1 plus, let's say, y square equal to 1 plus half y square, correct? So think of a binomial expansion there. And then use that. So this becomes x naught plus, right, half of y square. So this is half of 1 of the x naught. So this is, how do you say this? X naught, there's a, sorry. So this is 1 plus.
1 plus half alpha squared t squared over c squared.
Yes, that's correct. And alpha square, where is the alpha you saw? Or a square, you mean, right?
Yeah, a squared in this case, yeah.
So, yeah, I not reached there. I'm behind you guys. Right? Neglect the higher order terms. Neglect the higher order terms and write this as x naught plus half of the x naught cancels out. So it's c square, t square, and whatever x naught remains is nothing but c square over a naught, right? So c square over a naught. The c square in this case, exactly like the energy term when we were looking for the energy expansion, mc square plus half mv square, the c square cancels out in that kinetic energy term. C square again cancels out in this expression, and this is x naught plus half at square, which is a Newtonian trajectory, which is a parabola, and a naught, exactly the same a naught proper acceleration sits in there. And in this sense, and there's usually a vt also there, right? Initial velocity, but we set initial velocity to be 0. So in this sense, the hyperbola is a generalization, or hyperbolic motion is a generalization of a parabolic motion. So that's a neat little exercise. But one should say that this hyperbolic motion has lots of interesting features. This is like in Newtonian physics also, right? If you're doing any test system, the first thing you would test it with is uniform acceleration. So similarly in special relativity also, anything new, if you're ever doing, you want to, this is your test bed that and how does it behave under uniform acceleration. And in this case, the idea is of uniformly moving with uniform proper acceleration at every instant of time. Its acceleration and its rest frame is the same. So that's all, and we can finish 10 minutes early today, right? Any questions? Yeah, maybe questions.
Are we done for the semester?
Yeah, I think so. Yeah, thanks for listening. Yeah. Yeah, Angela is clapping.
That's a clap of appreciation for you, sir.
Yeah, Zoom has this. How do I?
The reactions button, and you clap, I guess.
Yeah. I don't know how to do this. Okay, where do you see this? Yesterday also.
Near the chat window, you have reactions, right? Like where you say chat?
Oh, in the chat window. So I have to look for the chat window, is it?
No, like along the same bar, chat, participants, share
Yeah,
screen,
reactions.
record.
Yeah, got it. Yeah. Okay, so I can also try that.
Yeah, there you go.
Did you? Oh, yeah, there you go. Yeah. Yesterday I was looking for this and I didn't find it. Okay, so reactions. Okay, good. So I don't get to play around with these things because I'm always on the on the stage. Okay, now I don't know how to gallery view. Okay. Okay, now I see all of you guys. Yeah, okay. So that's all. Again, thanks for listening. You guys were pretty participating, so good, thanks. And I think some of you guys, I'll see you again, I guess, some course I might be teaching.
So.
I did get a tentative teaching schedule.
I haven't looked at all classes yet. Are you teaching E&M next?
I think so, yeah, at least tentatively. These things change, by the way. It's very, very tentative. But yeah, I am assigned E&M and math methods, but I have been, the undergraduate math methods I'm not teaching, so.
Okay.
So I'm teaching 203 this time. So if any one of you is grading that, let me know. You should contact me. Yeah. So
cool.
That's one of those bigger classes. So that's usually more intimidating to me.
Mm-hmm.
Lots more emails.
Yeah, lots more emails and a lot more, I would say, you have to be telling the right thing all the time. I don't take the liberty to speak myself out. I'm not sure who likes the thoughts and who doesn't like the thoughts. I'm a little reserved. And because it happens in this big room, 440 auditorium, that itself kind of detaches the students. There's so many of them, and then they are at a distance. So I've seen that it doesn't give any room for any discussions, or it's usually very formal. Yeah, a lot more formal than the physics, usual physics courses. But it's okay. Yeah, and I'm teaching 203, the algebra-based courses.
Do you teach?
Yeah,
do you teach A or B? Is it both?
I taught both in the past many times, both A and B, both algebra-based and calculus-based. And it's interesting, the observation I made is that the calculus-based students have a better background in physics. They're more motivated in physics, but they don't show up in the classes or they don't participate in the classes. It's the algebra-based students who work more, who participate more, but the calculus-based students have a better background and they're more motivated, clearly. But I think the algebra-based students are more grade. I think for them the grades are important because of most of them take this medical test. What's that called? MCAT. Is that called MCAT? I think so. Yeah. And there the grades play an important role. So I noticed that they're more sincere students in a sense. You tell them something and many of them come back and do exactly what you're told. But I'm planning to implement this online homework this time, a new platform. Like usually I use WebAssign. Like one of the drawbacks in those courses is that my homework is slightly disconnected with what I teach in the class. Like in this course, I design my homework. So there is a clear connection between the homework and the classroom. But there I use the textbook problems, and then the online platform is expensive. So there's a lot of dissatisfaction among students, even though they like the online submission part because it's instant feedback, but they don't like the fact that they have to pay for it. And I also don't like the fact that they have to pay for it. So I'm going to consider using a free version of that, which will involve a lot of work on my part, that I'll have to type in all the all the homework problems. So I'm planning to do that, but I've not decided yet because it's a huge investment of time. I'm not very sure whether I want to consider that or not. So that's something that I have to decide in this summer. Yeah. But anyway, that's different.
Could you just use a different platform entirely?
Means I didn't understand the question.
Like I was just wondering if there are other platforms that are free, but it wouldn't require as much.
Oh yeah, there are lots of. Okay, usually there is no free platform. Usually the textbook comes with it.
Okay.
If you buy a textbook, they have this homework available. But the textbook, they make it extremely expensive. So what I usually say is that I recommend it. I use a textbook, and then I say that physics has not changed for last 300 years.
Yeah.
So you're allowed to use any textbook, and the homework will be provided to you, so you don't have to depend on the textbook for the homework. But this is the textbook I'm using, like in principle, like using in the sense, this is what is a signed textbook, and there'll be examples taken from there. Usually I bring out the problems also from the textbook itself. So students like it. It's not like this course where the textbook is not existing at all.
Right.
Less than existence.
But you have to choose a really expensive textbook for this course?
I don't choose it since this is a introductory level course at a university level. There is a committee that decides that, and it's a reasonable textbook. It's a good textbook. In fact, the algebra-based textbook is very nice, and it is one of the good textbooks among the lot. It also happens that the author is from SIU. He was there in our department just, I think, probably until 2011 or something. So he's from Carbondale. Most probably he's still around in Carbondale. I had never met him though, but it's nice to use a textbook from your department, and it is good also. Like it is one of the most used textbooks in the nation.
Very cool.
So that's surely, I'm not against using the textbook, but I don't make it compulsory. I say that this is the textbook and you're allowed to use any textbook you want. The problems will be, the only place where I really invoke the textbook is the homework problems and the examples, and that will be provided to you. And I provide them with my notes also, unlike these courses, graduate level. And the only place is that the homework problems are set by someone else, like in the sense the author's language comes in, and my style doesn't show up there. So there is a disconnect between what I ask in the exam and what they work on the homework. So I would like to change that, and that requires using a platform that I can edit my questions into.
I see.
And that the platform is fine. It was an easy choice. I'm going by the oldest platform, but just the fact that typing in everything is a big responsibility. So I'm not sure whether I want to take it up or not. So,
makes sense.
Yeah, so that's so.
I know that some of those, because I helped at the previous university I was at, I helped them write some questions for some of the undergraduate courses. And it was very difficult on an open platform because when a student submits an answer, unless it has well-defined bounds for what the answer should be, lots of times students will lose points.
That's correct.
Even though their answer is essentially correct, but they'll work in circles for days with an incorrect answer, which is actually correct.
Good. I know what you're talking about. See, this is the price you pay for online. Okay. Now, so the point is, physics, remember, involves you read the question and you play around with it, work on it. The intermediate steps are very important. And then you get a number. Eventually you get a number. And all these online platforms works with is that final number. It will tell you whether that final number is correct or wrong. Now, there is a traditional way, which is in my opinion, the best way, that, okay, you write the whole thing down, you submit it, and then one grades it and gives it back. But then that has this drawback that you do the problem on a Monday, you submit it on a Thursday, it gets graded and comes back to you on the next Monday. By the time you've forgotten the details of the problem. So that feedback, even though someone writes and gives you, is not as significant as this online platform where you put in a number and it immediately tells you that it's right or wrong. At the price that you might, there are two possibilities, that you might have got the answer very close to it. There is a software glitch and you did not get it correct. So one possibility is that you were right and the platform gave you a wrong feedback, or it could be the opposite also, that you were actually wrong and then actually it gave you a right feedback. But I still go with it because I have done this both ways, and I've noticed that the participation of the students is significantly higher with this online thing. So the feedback does help them, but there is this caveat what Jordan is pointing out. But I think that happens probably, especially with a well-tested platform. So I should say that I've always worked with a well-tested platform where many have used it. The chances of this happening is probably less than 5%. So then probably it's okay. But you're right, you're pointing out the right thing, that if I'm using a new platform, the error will be a lot more. And if it happens 20% of the time, then students can get really discouraged, especially if you're in the right direction and you go searching for the right answer. But I can argue that, yeah, even that search helps you. Even though it's a mistake of the teacher, if you struggle for it, I think maybe it's okay. But
if it's a big class, like we had a big class of like 40 students, and there were a few, almost always in like a 10 questions that we would make, 1 or 2 questions would be, you'd end up with 32 emails for each one of the questions saying, I promise this is an easy, I feel like I know how to do it, and I put the solution in and it's wrong. And then you come to find out it's something simple like the system only accepted 3 significant digits, and if you put 4, it was incorrect because it missed the margin of percentage of error.
I know this clearly, and I know what you're talking about. And I do give them a lot of options. My way of doing it is that I give them 10 choices, like 10 times they can attempt. It's not 1 or 2 times. So.
Oh, okay.
But yeah, you're right. I mean, yeah, I should think about it. Yeah, these are because it is a big class, they don't take it in the spirit. Like they have other things to do. It's not the only course they're doing, and they're not highly motivated either in physics. Yeah. So
one of the ones we had the most success with was, which requires a little bit more from the professor, unless you use like a platform that already has pre-written questions, but always having a practice question that is identical but different numbers, where they can work the practice problem as many times as they want until they get the correct solution, and then they can work the actual problem, and then the actual problem has like 1 or 2 submissions.
Yeah, I understand what you're saying. Yeah, good comments actually. I should keep all this in mind. Even though I've gone through it, you tend to forget this, and only when you go through it, oh, I shouldn't have done this. Okay, yeah, I should keep all this in mind.
Yeah, the practice questions I think worked best for us because it ended up with, we were kind of testing different things in this course, and it ended up being that when you use practice questions, students would ask less questions and they would just work the problem more and more until they got the practice question correct. And you know, you would only answer questions about the practice problem, and then the actual problem, they're left to their own devices.
Got it.
We liked it. I think that worked best. Writing our own questions it didn't work out well for us. It was very hard. But you're going to be better at writing a problem than I would ever be. So.
Yeah, I'm not sure. Yeah, because it's a big class, I worry, and it's more than 40 students. Sometimes, I mean, at least 5 years back, it used to be 100 students. these days it has gone down to 60 to 70 students. So it is a big classroom, and things go crazy if there are errors on the administrative end. Administrative in the sense of my end.
But you don't even have to make an error, but their submission could be incorrect because your parameters aren't fitting their calculator, you know, put in the number or put in the numbers, it spits out something that has, you know, if they round at 2 significant digits on one, and then they round at 3 significant digits on another, and then they round at 4 significant digits on another, well, then they're not within the 5% error that you want them to be, even though their process was totally correct. They just, it gets weird.
Yeah, I know. I mean, yeah, you're almost discouraging me from trying to do that. I get scared with these things.
I'm just saying, you can put in we put in a lot of time, and you could put in a lot of time to make it really, really good and make your questions.
It's not worth it either, right? I mean, I don't enjoy those things much. Yeah, but
and then
it's mainly for the students' sake that then they don't see the disconnection between the homework problems and the exam problems. So that's the main thing, main motivation there. We'll see. Probably I won't enter into it. We'll see. I think I have this whole summer to worry about. And what so Angela, you cannot go to India now, right? You said you were planning to go.
I wasn't planning on going for the summer anyway.
Oh, you weren't.
Yeah.
Okay. Then you're good. Then you're good. Okay.
But yeah, I happened to a couple of my friends. They were planning to go, but they had to cancel.
Okay. Avinash, what about you? You were planning for some summer projects, right? Did anything come up?
I applied to Lehigh University, and they said they are not able to take anybody from different university because of the health advisory.
So this has hurt you then in that sense, right?
Yes, they are only taking, they said they usually take like 25 students, but this year they're only taking 10 students who can work remotely.
Which university, Avinash?
Lehigh University.
Lehigh.
Lehigh.
Where is it?
Bethlehem, Pennsylvania.
Okay.
It's a good university in physics.
Yeah, I guess it might have hurt everybody's summer internship plans unless you're working in a computational kind of project.
Yes, that's what they said.
Experimental project, it might hurt everybody who's doing it.
But hey, they said they're not going to charge me the application fee if I'm applying for their grad program, which is good.
Okay. Okay, good.
Yeah.
So did they select you and then said that this is not going to work, or how did it go? Or everyone got this?
They said they're not taking anybody outside of the university, and they are only taking people who can work remotely, means computational projects.
Okay. Yeah, a lot of things happening. And what are your plans, Moses and Jordan? Jordan will be freer a little now, right?
Yes, I'll get to just work, and then outside of work, I'll get to research or study whatever is of interest to me, which sounds awesome.
Moses?
What will that be? Are you going to join a research group, Jordan, or?
I'm not sure yet. I'm not sure what my availability will be to actually be at the university. It depends on, what the stuff that I'm doing right now with, the magnetocaloric stuff is not going to probably be available, I'm assuming, this summer. So,
okay.
I'm probably going to build a solid state Tesla coil.
Okay.
And Have you ever seen videos of singing Tesla coils?
I have not.
Basically, you can hook up a guitar to a Tesla coil and you can play music through it.
Oh, that's very cool.
So
sounds neat.
So that's something that I want to do. So I've built single spark gap Tesla coils, and they're pretty cool. But I want to be able to do something with them. So I made a capacitor out of a giant bucket, basically a 5-gallon paint bucket, and I filled it with salt water, and then put motor oil on top, and then dropped 12 long neck Budweiser Select bottles down in the bucket, and then filled them with salt water, then pulled some wires out of them and created like a 12 nanofarad capacitor for, let's see, it's about 800 turns of wire, the one that I have right now, and it'll shoot a spark about 2 foot.
Wow.
It's about 380,000 volts out the top.
Ooh.
But you could touch it. You could touch because all of the resistance from the coils. So the current's really low, but the potential's really high.
Oh,
Wow.
You're building this in your home? Where are you building this?
Yeah, I just built it for fun. A lot of this stuff I just do whenever I have time where I'm not doing schoolwork, but and then I want to build.
It's amazing that you find time. Yeah.
Yeah, when I'm not in school, it's not so bad. I have time because I'm just working, and all the time I would devote to school, I would just devote to building something like this. And I also want to build a multi-axis. Gosh, what's the name of it? Why can't I remember what it's called? Acoustic levitator. I want to build a multi-axis acoustic levitator as well. Just that one.
Yeah, you showed me that. That was neat.
Yeah. Yeah, the acoustic levitator was fun.
Yeah.
I'd never really messed with Arduinos and stuff before, so I got to learn a little bit about that whole process.
Cool.
There's a lot of people, like the University of Bristol put out a lot of articles about how to build, basic acoustic levitators, but there's nothing really out there for the multi-axis. But it'd be cool if I can make it, because you could actually take those little styrofoam balls, and then you could, with a multi-axis one, you could actually, levitate a wave function inside the acoustic levitator. So you could like change the frequencies, and then you could show, what a wave function would look like between these, just used by pressure waves. Kind of cool.
That would be very cool.
Yeah.
What are your plans?
It'd be cool to be like, this is this is this type of wave, and then you just throw some styrofoam balls out there, and you're like, this is what it looks like. That'd be cool.
Yes. Yeah.
Moses, what are you doing this summer?
Well,
Do you still remember our MATLAB thing?
Oh yeah. So we'll try to learn some MATLAB. Yeah, I mean, I need to join a research group as well. So probably this next week I'll start meeting with some of the other professors. I've spoken with Dipanjan already. There's a fair chance I'll join his group. He's got some funding for summer research. I'm gonna talk with Bumsu as well. I mean, I'm interested in learning, a little bit about the work that all of the groups are doing. Yeah, I guess I have a feeling I might gravitate more towards the experimental stuff. So yeah, hopefully I'll do some summer research, and that would be cool. And also, yeah, I'm potentially going to teach some English on an online English teaching platform to make some extra money.
Cool.
Yeah.
And where will the students be across the?
Yeah, well, depending on the platform, but probably from China.
Yeah.
China. Okay.
Yeah, and like really young kids. So.
Have you done this before?
No, I've never done this before.
Okay. Oh, great. Good.
Yeah.
And
Angela, you will be working with
Dr. Bird, yeah.
I suppose, right?
I don't know if I'm going to get paid or not, but I'll be working.
Yeah. Hopefully. Yeah.
So Professor Shajes, what are you doing over summer?
I will get to do full-time research. That's the luxury
at SIU?
I have, so I keep my... at SIU means I don't need any yes in SIU because I will be here. Usually I go to Norway, so I was supposed to go, but then they temporarily, at least in March, they said that they are temporarily canceling all the visits, and I don't expect it to change at this late stage. So yeah, I'll do whatever I used to do there here. It doesn't change much because it's theory, so I can do it anywhere I can. But I used to do it in Norway because they used to pay me, so it is necessary that I go and stay there. So that was the main reason why I used to go. So it'll be the same work I'll be doing, but here, yeah.
What are you researching?
Oh, what am I researching? So the main, okay, let's see. There are two pending problems which is going on for the last 3 years. I think that's what I think I might pick up. One of them I'll pick up is one of them is a recent one. I think I got motivated in it from Dr. Mazumdar. That's a topological insulator. And you can talk about what happens, like Casimir effect is, have you guys heard of Casimir effect?
I have.
I've heard a little bit of it.
Yes.
So in very simple terms, if you have a capacitor, right? Think of parallel capacitors. Let's say vacuum in between, there is no material in between, two parallel conducting plates, right? Usually you have a positive charge on one end and negative charge on the other end. And it's very clear that they will attract each other, right? But now imagine a situation that there is no charge on either of the parallel plates. And the expectation, naive expectation, is that there is no charge, and imagine that there is no mass either. That means to say that you're switching off gravity, right? Or we're not considering gravity. So electrodynamically, electromagnetically, let's say, this is not supposed to attract using our introductory level or whatever physics that we do, unless you invoke quantum electrodynamics. This is not supposed to attract, but it turns out that it does attract. You can calculate this. And this is typically done for either dielectrics or magnetic materials or conductors. So that's Casimir effect, basically. Two parallel plates attract. And why do they attract? Because there is vacuum. Vacuum as a structure. Vacuum is not the way we imagine it to be in empty space. It can create and destroy particles in them, right? That's the basic idea. And that causes this plates to attract. And now, since topological insulator has come, there has been a lot of interest in, okay, consider these materials to be topological insulator. They are a new kind of materials, not an insulator, not a conductor. Like that's the typical two extremes we see, right? There is one parameter that decides the property, electric property. One end there is an insulator, the other end there is a conductor. And now there is a new feature. Basically, the idea is that usually electric field causes polarization in electrodynamics. When we study in the early part, those of you who are not taken the first 1 month, we talk about you provide an electric field, charges will polarize. If you have a positive and negative charge, they will polarize the charges. But now in a topological insulator, if you provide a magnetic field, it will polarize, electrically polarize. That doesn't happen in classical electrodynamics, that you provide a magnetic field and it will electrically polarize. That doesn't happen. And that's the characteristic of a topological insulator, which shows all this interesting property that it is topologically, or it's on the surface, it is a conductor, and in the bulk, it is an insulator. So that can be tried out on a Casimir context. And this has been done by others, but remember, Casimir effect can be derived in various techniques. So I'm more on the very analytic end, and I have attempted this in the last summer, and it doesn't smoothly go through. At least I haven't got the thing yet. So it seems like there is something missing. So that's one thing one pending. And another project is if you have a conductor, and just if you have a aperture in a conductor, and you keep a small atom on top of it, it seems it repels in a certain regime there. And that has been using symmetry arguments and using computations, physics, you can actually show that that happens. And I believe that because I can see that that will happen, but analytically the expression doesn't exist. Like start from the scratch and then do it, it becomes hard to do the evaluation. So, and it's an open standing thing for last 10 years. And I have been attempting it for the last 10 years, you can say, but off and on. And it seems like I can, if I spend time on it, I can get it done. So those are the two important problems if you want, but all related to Casimir effect. And I do keep simple things here.
The second scenario where there's an aperture in
yeah, I can. Yeah, I went very quickly. I can actually.
That's also that's also related to the Casimir effect.
Yes, yes. So what happens is that Casimir effect usually until 2010, okay, until this very recent, right? You have two parallel plates, right, and no charges, nothing, and they attract. Think of this as an attraction. In fact, you can take any two objects, you can show any two objects, they will always attract. Okay, so so it was always thought that, okay, two objects, they will always be attractive. And this led to the idea that if your Casimir effect plays a big role if you're working in micro, less than like 100 nanometer regime. So if you're making a processor at that small scale, then this is attractive. This causes stiction, everything sticks, right? So then technologically, everyone wanted to know, can you guys, so everyone looks up onto theory people and say that, okay, can you come up with some way we can avoid this stiction, right? And there was a lot of funding in the first decade of the century on finding a repulsive Casimir force. And the answer to that, one of the answers to that, there are many ways of doing this. One is the topological insulator. One way is that a very counterintuitive thing. If you have a plate, so you can see this. If you have a plate and then you have an aperture in it, right? And think of this as an infinite plate and there is an aperture in it. And you bring in a small elongated atom, like elongated in the sense if you're thinking of a conductor, it has to be elongated. Otherwise, think of it as an atom, a polarizable atom, right? Let's make it simple. Let's say a polarizable atom.
Aperture means like a cavity of some sort, right? Am I not understanding? Aperture means
this
cavity.
is cavity in the sense it's an aperture. This is a conductor. Does that make sense? With a hole in it.
Yeah, okay, that was my question. Yeah, like a hole.
Right, yeah. So I use the word aperture. So this is, let's say, radius A, and this is height h. So this has this interesting feature, and they couldn't analytically get this, but using symmetry consideration and computations, there's a lot of, like it's easy to do these things because it gets hard using computation. If you know how to remove divergences, like all this is, you say, plagued with divergence, like so many divergences, it's very easy to make mistakes. But if you do this all correctly, it turns out that if H is very much larger than A, right, then when H is very large, it's attractive. But when you go very close to the aperture, it's repulsive. Okay? And in the beginning, it was so counterintuitive, no one accepted this. Like this was 2010, this was done. And even first time when I heard it, I didn't believe this. But then there were various ways, like I could do this in a dielectric approximation. So instead of a conductor, make this all dielectric, and immediately I could do that, and it becomes very simple, and you could see the same effect there. So far, and I involved an undergraduate student here in SIU. That was my first days here. He also worked on that, and it was kind of nice how this shows up for H less than, basically less than, I think it is 0.6A or something, then it comes out to be repulsive. And then the question comes, can you do this for a conducting, for the problem that's going discussed? Can you derive this from the scratch? And it's all the physics that you need is electrodynamics course, graduate level electrodynamics course. And it seems close, so yeah, but I've not done it yet. Yeah. So off and on, I think I spent good amount of time on it. Yeah. And I think at least the ideas I wrote, I think I did publish 2 years back. I made the progress available, but I didn't solve it. Yeah. So actually, yeah, since you guys talked about hyperbola, right, today, so I go the complicated way, right? So you can consider two hyperbolas, and then take the eccentricity of this tiny, make it smaller and smaller. So think of this as two hyperbolas. So you work in hyperbolic coordinates and think of this as two hyperbola, and then you squeeze this, make the eccentricity of this hyperbola smaller and smaller. In an extreme limit, that becomes a plate. Right? And there are reasons to do this for hyperbola instead of a plate, because it's very hard to get the Green's function for a plate with an aperture in it. Extremely hard problem. So that's not easy. So instead, you take a surface and try to get the Green's function. So you're doing a more complicated problem, but apparently easy for the mathematics. And then you take the limit in which two hyperbolas can become a plate with an aperture. So, and this has, the main idea is that this has axial symmetry. That's what you want to exploit. So yeah, so that's the kind of problems I keep myself involved in. Yeah.
I have one question. Might be,
yes, Avinash.
Might be a dumb one, but
no.
But again, I got a question, so I gotta ask. So, do photons show Casimir effect?
Do photons what?
Do photons show Casimir effect? Because
okay, so
photons don't have mass.
Okay, the point here is that, so when you think of these two plates, the way you want to imagine this is that even though this is neutral, for a moment it is possible to create a positive and a negative charge. Right? Think of statistically possible. What is it? Fluctuations, right? Quantum fluctuations cause a positive and a negative charge, a neutral atom to go separate out. The moment they separate out, there is electric field, and electric field is nothing but photon. Okay, at a very simplistic level, electric field is a classical picture of a bunch of photons. When the number of photons is very large, it's electric field. So we are talking about electric field going, so photons going from here and then reflecting back, right? They keep oscillating up and down. So we are talking about photons are there in this, and that's what causes the that's a backbone of Casimir physics. So the way you will see is that electric, so what is vacuum? The average of electric field is equal to 0. That's how you define vacuum, right? Because there are charges there, there will be creation and annihilation of particles, so there's always electric field in there. But on an average, electric field is 0. Okay, that's good. But that doesn't mean that the square, or in fact, this quantity, the adic of this is not equal to 0. And remember, energy is square of electric field, right? Energy, electromagnetic energy is half epsilon E square, right? So simply because you have vacuum, the average is 0 does not require, remember, average doesn't imply the variance to be 0. Doesn't imply this, so that means there is energy. The moment there is energy, there is force. Right? Minimal, if you can find a minimum energy to that, there is a force. So in that sense, yes, these are photons, and this is related to the average of the photon electric field. That's what the energy is. So in that sense, yes, it is. But while you're asking this, maybe your question is that suppose you have 2 boxes of photons. I don't know how you will imagine that. Okay. And they have to mediate. I don't know. Maybe you can talk about the following problem, like there are photons here. For some reason, they're confined. And there are photons here. And I don't know how you will confine them. But then photons can interact. Like what will photon interact with? Like photon have energy. You can think of gravity, right? So this interacts through gravity. Right? Photons have energy, like photon gets attracted towards a planet, right? When bending of light, think of that. Right? So in that sense, you can think of this. Yes, it might be doable. And this might be related to what is called Unruh effect. So yeah, it's a good question. And I would say maybe partially it is done. But the moment gravity comes, remember, it is not quantum. We don't know how to quantize gravity. So, and this is a quantum effect we are talking about. So there will be lots of. So I would say the answer is, yeah, it is an unsolved problem, if you allow me to say that.
Okay.
But so, look up Unruh effect also. Unruh effect is not, it exists for the last 30, 40 years. And this is exactly the context it fits in. It's basically about a black hole.
Is it UNRUH?
Yeah, UNRUH. And this is actually also called Fulling Unruh. I mean, he's one of my collaborators, so it's usually dropped, so I shouldn't drop it. Yeah, it's called, I think it's called Unruh Fulling effect or Fulling Unruh effect. Yeah, he's in Texas A&M. So we had a speaker yesterday from Texas A&M, a very leading person, and he's one of the persons who suggested that. But with that, I would say it is open question. There's a lot of open-ended problems in there. It's a hard problem, very hard problem. But yeah, good for you guys are young, and those are the problems you want to pick. Yeah.
I remember last.
Hey Moses, you could fill the void.
You could. Sorry, I didn't understand that. Avinash.
I said you could fill the void.
I could. No. I mean, you're the younger ones, right? I always say that I've passed my time. It's hard to do solve important problems after a certain age, statistically speaking. So you are in that age gap still. But anyway, that's a joke. Yeah.
So I remember having a conversation with you last semester about this. And
yes,
I remember doing some research later, and there were some people that talked about instead of the vacuum, like a vacuum type energy, it was rather like relativistic van der Waals forces instead.
Yes. Yeah. That's the same thing, different language. Okay, so the way to see it is that there are 2 ways of interpreting this, correct? So one way to look at this is that the fluctuations in the electric field is 0, average is 0 and square of it is not 0. You can also think of it as I just now started with that there are charges in the plate. In fact, there are dipoles, right? So there is a dipole. On an average, these dipoles are 0. Like the fluctuations in these dipoles are 0. Like think of an atom which has a positive charge in it and a negative charge. The center of the positive charge sits on the center of the negative charge. That's a perfectly uniform, spherically symmetric atom. Right? Think of a helium atom. That's how it behaves. But there will be fluctuations. There will be disturbances. It will move away, right? So for a temporarily, there is a dipole moment that you create. So on an average, that is equal to 0. But the square of that need not be 0. And that's van der Waals effect.
Okay.
Right? But van der Waals is a very extreme limit in the sense it's not relativistic. It is. It deals with very weakly interacting or weakly electric properties. You can say weakly dielectric. So that if think of this as extremely relativistic and conducting materials is what Casimir effect is. If you talk about dielectrics and speed of light is gone, no relativity, non-relativistic Casimir effect is van der Waals force, or what you said, relativistic van der Waals force is Casimir effect. That's true, completely correct. Yeah, that gives a lot of interpretation ease there. Like there's an insight in there. Correct.
There was something about like its ability to describe the system microscopically instead of macroscopically, or I don't remember. It's been a while since I read about it.
Yeah, probably. Yeah. Like there are interpretations. Like how it goes is that okay, maybe historically speaking, Casimir first time did it using this way, like this method, right? And the calculation went for pages. Like he did it with Polder, one of his students, I presume, and the calculation is very tedious. It goes for probably 30 pages or so, and a nice little result. He had it for 2 atoms. But then he discussed with Bohr, apparently. They went for a walk, and this is what most of the time interactions with Bohr are apparently like when you read history. And he apparently, according to Casimir's own words, he mumbled, okay? So he mumbled that maybe this has something to do with 0-point energy. It's not an explicit statement he's made. He's just maybe, or maybe he said, he did not even say it and Casimir just heard it. Either way, that made Casimir think in this terms, and the calculation was finished in, let's say, 2 pages. Like there was a significant difference, and conceptually, this has a bigger impact. Like this has the idea of 0-point energy in it, and that is conceptually big deal. It is bigger than what we are talking, like the force itself is just happens to be a system we are talking about, but 0-point energy has a meaning outside 2 parallel plates attracting. And
Gotcha.
that's what everyone is after. That's a big deal. And for example, if you're talking about cosmology, we have dark energy. I think Moses sort of gave a little thought on it. If you're talking about dark energy, one of the big candidates for dark energy is the Casimir effect of the whole universe. But the unfortunate thing is, if you calculate it, it is hundreds of magnitude off. So it doesn't fit in the naive way of doing it. So if one is clever enough and one can fit in something, be clever, then you have the biggest unanswered question in front of you in that sense. So yeah, it's I would say this is nice, very good, very convenient, but this has a bigger fundamental question being addressed there. So usually everyone usually likes to put it in this framework. That's
Gotcha.
Yeah. Okay.
So
It's 11:30. Yeah, go ahead.
I was just going to ask, is Prachi also doing the same research as you?
Yes, exactly. It turns out that she does exactly the same thing. We collaborate.
That's good.
Or I would say that Prachi is my wife. For those who don't know, I think yeah, Avinash has met. I think Jordan, you're the only one who has not hasn't met Prachi. She works with my old advisor still, and the only difference is that she works on more problems than me. Like I'm confined to limited number of work, and I think she, like I say, that I usually blame it or give the excuse that she had the opportunity to work with more number of people, and she did more postdocs than me. Like I didn't get the opportunity to get so many postdocs, so she worked with a lot more people and works on a lot more effects related to Casimir. But pretty much the same thing, yeah. Most of the time, if we are in the same place, we collaborate and we write the same thing. So it's convenient, yeah. Being in the same house, there is a convenience, and luckily, there's not too much mismatch of thoughts there.
Mm-hmm.
Yeah, so that works out well.
You guys talk about research all the time.
That's, yeah, I would say yes. Apparently, yeah, it's convenient. I would say it's convenient to whenever there is a thought, immediately put it. Yeah, sure. Yeah, I think it does happen a lot. Yeah, yeah. I think it's good. Yeah.
All right, bye. See you, everybody.
Okay, yeah, I think
yes, hopefully we'll see you, not virtually and physically, the next fall semester.
Yeah, hopefully. I too agree. Yeah, hopefully all this is over and we can get to normal world. Yeah.
Yep.
And good luck until then, and thanks again for listening. And,
thank you.
Yeah.
Thank
you.
Thank you for putting the board together in your house and recording the video lectures. I appreciate it. It's been very helpful to me.
So. Thank you for relaxing on the deadlines and constraints and everything. That's been kind of helpful with everything that's going on. Yeah.
For sure.
Yeah, I think I would say that I was late in understanding that, but yeah, I think that worked out well. I think probably pointed that out, that students are also facing the same problems, that they're not having all the free time, because it didn't go through. Yeah, so I think it worked out well. Yeah, but still nowhere close to classroom.
Yeah.
But yeah, we will survive. Yeah. But good luck, and yeah, if possible, keep in touch. Enjoy.
Yeah, definitely.
Okay.
Okay.
Bye.
Bye, everyone.
See ya.
See ya, Avinash. See ya, Moses. See ya, Angela.
See you later. Yeah. Bye.
Avinash, did you say you wanted something?
I meant to ask you this before, but we got sidetracked. Has Casimir effect been physically observed?
Yes, that's why it was very actively pursued recently in 98. It was experimentally verified to, let's say in 98, it was experimentally verified to about 15% accuracy.
Mm-hmm.
And these days it is experimentally verified, at least everyone says it's within 1 or 2%, but even if you want to be conservative, surely within 5% error, it has been verified. So it surely exists. These days, no one doubts it.
Okay.
Like it's very clear that it exists, everything is fine. Now it is a matter of getting very clever with it, or technologically, there is a lot of interest because you can really make nano machines out of this, and people are really working on that. And then also because of the dark energy concept, there is a lot of theoretical interest in it. But mostly this is not clean physics in the sense there are divergences, there are lots of infinities, it is hard to deal with it. Mm-hmm. So mathematically that's very challenging, and that's what I concentrate on. So how to handle the divergences there. So that's my most of the time I spend is on that. Did I answer your question?
Yes, that answers my question. Yeah, thank you.
Yeah. Good. Yeah.
Okay, I'm gonna head out. So have a good day and see you tomorrow.
Yeah, thanks. Yeah, see you tomorrow, Avinash. Yeah.
Bye.
Enjoy. Mm-hmm.
You
Bye.
too.